Okay, all right, so I will hold it in my hand. Okay, so what I would like to do, I would like to maybe find a better way of analyzing this kind of data. So I guess what I'm saying here is that count processes are not really easy processes to analyze from the empirical perspective, and maybe we shouldn't do it if we don't have to. Okay. So let's step back and let's try to look at the so-called SIR process. And I will call it a micro model, because I will try to think about it not from the point of very, very large population and aggregated numbers of infected, susceptible or recovered, but I will try to think about it from the point of view of the underlying stochastic equations. And the reason that I do this, I would like to connect it to the data somehow. So what is the stochastic process that you can sort of think about when you're looking at the SIR model? This is the so-called stochastic version of an SIR epidemic, and it's actually a very simple discrete process, which is a special case of a class of processes that are called chemical reaction processes. These are basically discrete space, but continuous time Markov processes in their simplest setting. So the idea here is that I will, think about this process in terms of two reactions or interactions that will be happening at random times that are basically equivalent to a movement of this discrete process to a different state. So this process will be described in terms of the number of molecules, I call it using chemical nomenclature, I will call it molecules, the number of molecules that are labeled S and the number of molecules that are labeled N. I'm assuming that these molecules are diffusing in some large compartment, and after a random amount of time, the exponential amount of time in fact, they will collide with each other, and as a result of this they will instantaneously give rise to another set of molecules. So this is a very simple way of describing chemical reaction model, and here I am basically looking at two interactions. I have the molecule labeled S, that stands for susceptible, and then I have a molecule labeled I, that stands for infectious. And if these two molecules will get in close proximity, then instantaneously the S label will be erased and the I label will be introduced instead, and that will basically change the state of this system, which is described by the number of S's, I's, and R's, which I haven't defined yet, in the sense that it will basically add an I and erase an S. Okay, so I can describe in this way also the second equation. The second equation simply states that after, again, random amount of time, this label I will be replaced by R. Okay. And then the notion is that there is some rate at which these reactions are happening, and the rates are following something which is called the law of mass action. So it basically assumes that there is all of these molecules basically they have an equal probability of interacting with each other. The system is mixed and in some kind of thermal equilibrium. So it basically means that that the rate is proportionate to the number of molecules of S and I for the first reaction, and just to the number of I for the second. So this is just a standard decay law. So the so-called basic reproductive number, which is an important quantity, is the ratio of these constants beta and gamma to each other. So let's take a look at this model a little bit more probabilistically and formally. Okay. So one way in which you can describe this model formally is by introducing certain Poisson processes and writing explicitly what the trajectory equation looks like. So there's a couple different ways of doing this. One of them is by writing out either the generators of this process or by writing out the so-called chemical master equation, which is nothing else but Kolmogorov forward equation. But here I am actually using a different method. I am explicitly writing out how this process behaves. So the so-called trajectory equations are basically given in terms of Poisson processes and certain rescaling of times of these processes. So basically what I'm looking at is I have this triple SIR, which is the state of some collection of units at time t. I'm assuming basically that I have these initial conditions over here, and beta and gamma are not changing over time, they're fixed. And I am writing out the equations that now will be describing the evolution of this random system. So after starting with these initial conditions m and n, the S will be changing in the following fashion. It will, whenever it interacts with I, it will basically decrease. The discount S0 will decrease by 1. So that basically means that if I introduce the Poisson process yi, for which the argument is this scaled beta and the integral from S and I, then I'm basically looking at the rate of the process, which is exactly as I have written it before. Okay? So this is sometimes known as the rescaled time Poisson representation. And in fact, the interesting fact about this is that by the so-called Watanabe's theorem, basically every Markov process can be represented in this way, in terms of the rescaled Poisson process. So this is actually quite a general representation that's useful for looking at counting processes in some generality. And then in a similar fashion, I'm looking at i's. So what happens to i's is the i's are increasing by changing this S labels into I labels. So this basically means that I'm switching the sign on this Poisson process y1. But then the i's are also decaying at some rate gamma. So basically I have another Poisson process, which now I will assume is independent of this other one, which has the rate as follows. And then r's are just the keeping track of the number of recoveries. So I am basically collecting all of these y's that I have, all of these i's that I have lost through this process. So this basically just tells me that I am looking at time t at the Poisson process that has this rate. So the assumption here, which is important, is that these S's, I's, and R's are really following the law of mass action. So it means that the system is really well mixed, well stirred. I didn't say that, but it's kind of implied. If you have any questions at any point, and if I seem not to make much sense to you, then please ask, because I sometimes don't quite.
In case of Ebola situation,
yes.
So I is going to be the infected people, but R is the dead people? Or?
Yes, so R would be removed, so in whichever way. In fact, in Ebola it's a little bit more complicated, because it turns out dead people are actually very infectious. So in the setting of Ebola, this model would have to be slightly modified. But, you know, I only introduced the Ebola example to tell you a little bit about real data and the problems with real data. I do not, this particular model is maybe too simple to be able to immediately apply it to Ebola application. I want to talk about something slightly different. But yes, in the Ebola case, R would be removed. So that would be individual who is removed for whatever reason. This individual either recovered and attained immunity and is no longer a susceptible individual, or the individual died. In that sense, that individual is also removed from the population. But again, there is a twist for the Ebola because of the nature of the disease, that the dead individuals are actually very, very infectious. So that was one of the problems with the funerals, for instance, for Ebola victims. So this model, in order to describe accurately Ebola outbreak, would have to be modified slightly to reflect this. And in fact, it's not entirely clear whether law of mass action is appropriate. In fact, we have shown in some examples that it's not. And that's part of the reason that the CDC didn't get it right. But again, the idea here is that R's are just something that's removed for whatever. So these are these molecules or individuals, if you will, that are removed from your model. Okay. So a standard way of thinking about these trajectory equations is by means of something which is called the Gillespie algorithm. So a Gillespie-Doob algorithm, actually, or I should say Doob-Gillespie algorithm, is a way of generating this kind of stochastic process which is continuous a time discrete state space by means of doing a very simple manipulation of the rates as well as the exponential random variable. So the idea here is that we're using some basic properties of the Poisson process that allows us to simulate the appropriate Poisson processes. It turns out that in the particular setting that we are concerned about, you can basically do two steps of these simulations independently of each other. So the first step would be the simulation of the next time of the reaction, so the time until the next reaction. And then independently of that one continuous variable, you would simulate another one which will tell you, which will be discrete, and it will tell you which reaction actually happened, either the first one or the second. And it turns out that that's actually equivalent to asking about which of the two exponential random variables will happen first, if they're independent. So it basically gives you a nice, very straightforward way of simulating this trajectory that I have just written in terms of your Poisson processes, and this was one of the contributions of then Gillespie to sort of stochastic chemical reaction system. It turns out that this can be useful in various aspects of mathematical biology. And one of the things that many people have been interested for a long time in is how do you approximate some of these Gillespie steps if you have a very, very large system with very many different, very rich state space, whether there are ways in which you can simplify it. And we have also worked on this with some colleagues for quite some time for different reasons. But again, that's not what I really want to talk about. Okay? So let's look at this completely differently. I don't actually want to work with Gillespie algorithm because that's the standard way in which people do this. The problem with the Gillespie algorithm is that it's actually fairly complicated and it's difficult to use for fitting models. So I would like to propose a different approach. And this approach is based on something which is called a Selecki construction. It actually is a construction which is equivalent to the Gillespie algorithm, but it uses a slightly different set of tools, even though ultimately it's the same. Okay, so this Selecki construction, which was written in this paper in 1983, and I don't necessarily believe that I have seen many citations of that work actually. I think that there wasn't that many people who have spent time looking at that very simple idea. So Selecki's idea was, let's just use a different or have a different way of simulating our process, and let's do it as follows. Let's basically say that we have, as I did before, we have m individuals who are susceptible, and I also have m individuals which for whatever reason here I am denoting with negative numbers, negative m-1 up to 0. So this is the negative labels basically mean that I have at time 0 these individuals who are in the infectious state, right? Otherwise I would have a trivial dynamics because I would have no infection. If I have no infection, I have this first Poisson process would have a rate 0 and there wouldn't be anything interesting.
Negative m-1 means there are initially m-1.
So I go up to 0, so there is actually initially m.
Initially m.
Yeah. Again, I borrow this from Anderson and Britton's book. I'm not sure if I like these labels, but that's how they labeled it, so I kept it.
So it's index.
Yes, it's just the index of that particular m. So you have m infectious individual and n susceptible individuals. The point is that the reason that these things are labeled in this way is that we really are only interested in what happens to the susceptibles. So m is these individuals who are already infectious. They will recover with the second Poisson process at some point. The question is when, and then the number of these infectious obviously affects the dynamics of these susceptibles turning into infections. So that's why they are important. So Selecki has proposed a very simple algorithm for doing something which is equivalent to Gillespie simulation model. Basically said, okay, so let's, for each one of these susceptible individuals, let's basically create independently an exponential random variable with some unit rate, and let's call this thing a threshold for that particular individual. And then let's define this object. So what this is, it's a cumulative function that adds up to time t, all the individuals that are infectious. Okay? So this is a step function, which will basically increase or decrease depending on the number of individuals that are in the I state, including the initial M individual. Okay? So you can think about it as some kind of cumulative infectious pressure. This is called cumulative hazard function in survival analysis. But the twist here is that this quantity is random. Okay? So this is actually a stochastic process. And then what Selecki has done, he has said, okay, so now I will run my epidemic by basically comparing these threshold random variables Q's, which were independently generated. I will take the order statistics, so I will order them up from the smallest to the largest, Q, threshold. And then I will basically look at the AT function. So this cumulative hazard. So here I just shown this when m equals 1 and n was equal 5. So this is 5 susceptible individuals. And I start at time 0 with 1 individual infected. So because there was 1 infected, this AT was 1, so this was a linear function for a while, right? So this was basically a line. And at this point, I have crossed the threshold of Q1. So then I have made Q1 infectious. So that Q1 basically became infectious. I had 2 then. So the slope of this line increased. So I'm basically here. But then the first one recovered. So then the slope again became 1. Kept going. It reached the second one. So then it again raised and so on and so forth. At some point, I have basically leveled, meaning I have run out of all of the infectious individuals and my hazard have recovered. So I have no more opportunity to climb up, and these 2 individuals survive. Okay? So this is a representation of the Gillespie algorithm using this idea of random hazard. Okay? Then you could ask, why would you want to do something like this? The Gillespie is so nice and so quick, and here you basically have to calculate these things which are not always necessarily immediately obvious how to optimize, and why would it be an interesting way to do things. So I claim that there is some interesting concept here that we are missing when we're looking at the Gillespie algorithm itself. And this concept is basically exactly this. So let's look at what is it that, so why is it that this is an interesting picture? Because in my mind, what's happening here, we're switching. We're switching from counting individuals who are infectious, susceptible, to looking at the times at which these various individuals are moving from one label to another. Okay? So we basically are rewriting this problem in terms of the times of failures. So that's survival analysis. That's an approach that statisticians like to take, which is a little different from what the Gillespie algorithm does when it basically looks at counts of species over time. Okay, so that's one. So basically, let's look at this a little bit more carefully. So it's not that difficult to see that if I have had an individual who was uninfected by time t, then conditionally on the history of the process, I can actually, this individual will be only affected by this history through this quantity AT at time t. So if I condition on AT, I can write here that this probability of Q is greater than AT, which is basically telling me that this individual Q has survived beyond this time t, is this, because this was, remember, this Q was exponential with rate 1. So that basically tells me that this conditional now survival function of capital T, when capital T is the time of uninfected individual to get infected, is basically described by this random hazard function. So this is e to the negative AT. Okay, so another way of writing this somewhat informally is this. Okay, so again, so what? So I just have a different way of writing this set of equations in terms of this function at. So I have basically moved my problem from one place when I don't need to simulate that many continuous and discrete random variables to something else when I basically have to simulate these hazards anyway, or at least understand how they behave. So maybe this is not such a useful thing to do, but it turns out that that particular representation can be simplified, at least approximately, can look much simpler in very large populations. And that's kind of where I'm going with this. So I would like to use this representation, not in the particular setting of 5 susceptibles, but in the situations when I have a very, very large numbers of susceptibles. Okay, so when I will have a very large system. So let me briefly remind you what happens in very large systems. So we have, in general, the notion of the law of large numbers, which is not different just by the definition of the Poisson process. This is one way in which you can think about the law of large numbers here, is that if you rescale this variable y in this way, you basically end up with a deterministic quantity. And in fact, this convergence, I'm not very careful here about writing these things out, but in fact the convergence is at least in probability and uniformly on every compact interval. So if I rescale my stochastic trajectories, if you remember how I was doing this earlier, I was basically writing these Gillespie stochastic trajectories. So if I will now rescale this process by dividing everything by n, where n was the initial number of susceptibles, I claim that I can need to move it forward. I can obtain the classical law of large number version of this process, which will give me the standard SIR. So basically, what the rescaling does and sending n to infinity does, it basically makes these quantities on the left-hand side in the limit deterministic. And on the right-hand side, I am replacing these Poisson processes that I had earlier with their rates. So then I get integral equation. That integral equation, if I differentiate and apply the initial conditions here, I am assuming that this m over n quantity in the limit as n becomes large converges to some constant which is non-zero, so raw. So they're of the same order. So basically I end up with this classical equation, 1927 Kermick-McKendrick model. This is basically one of the most successful equations in mathematical biology. It's a very, very simple nonlinear system that most of the math biology students have seen at some point. And in fact, a version of this system was used by CDC to make predictions about Ebola. So what I'm saying is that that stochastic process that I have just described earlier, if you scale it, it converges in some appropriate sense to the solution of these differential equations. Okay, so that's good, but how is this connected to what I was telling you earlier about Selecki construction and everything else? So I will explain in a moment. In the meantime, let me just show you how these deterministic and stochastic quantities look like. So the rugged curves are typically in some kind of large domain, the realizations of the stochastic process. It looks a little bit like Brownian motion, but in fact it's just because of the poor resolution of this picture. This is a discrete system that has a set of jumps, and the smooth curves are the solutions of the differential equation. So the idea is that on average, these stochastic trajectories, if you have some of them and if you average them out, they will basically average out to these smooth curves. Okay? And in fact, if you will increase n more and more, then these rugged trajectories will become smoother and smoother, and in fact, in any sort of sensible way you can measure it, they will get closer to the deterministic. So that's the idea. This is the Poisson law of large numbers at work. Okay, so basically this is something that that I have, which is a good property, which basically means that if I take my stochastic process, Gillespie-like stochastic process, I will end up in the large limit with this SIR equation. So how is this related to this writing that I have just made over here? So notice that this AT quantity I have scaled in such a way that I here have the integral over I over n. Okay? Now, what I know from the law of large numbers that I have just shown you, that in fact I over n on every finite interval, for instance, will converge as n is becoming very large to a deterministic quantity. So if I will take the limit of this AT as n goes to infinity, I will obtain a deterministic value. So what it means is that basically that equation that I have at the bottom here, the equation for the failure time, it will become non-random in the limit. Okay? So that means that I can use this fact to create a simpler version of the Selke construction when this graph will be taken at n infinity, and it will in fact become smooth. And in fact, we know exactly what it will look like, because it looks like the collection, it's a summation of these AI units divided by n. So this is integral of the limit of I. So the integral of the limit of I by that differential equation is actually, if I write it in this form, or in this form, if I take the integral here, it's just R. So this hazard function, the cumulative hazard function, is basically a rescaled version of the limiting RT in this differential equation. Okay? So that means that I have a representation of this original process in terms of something which is quite simple. So let me try to go back and recap what I have just constructed. So I have told you that I've basically now have this time until the transfer, or until the relabeling of S into I, in terms of this limiting hazard function, which basically looks like the limiting proportion of infectious in the deterministic model. But that also means that I can rewrite it in this way and now interpret this S not as the proportion of susceptibles, but as the hazard function of the time of failure of a susceptible unit. It's not exactly a hazard function, because this quantity, and it's sort of obvious from these pictures, from these equations here, maybe a little more, but it's close. Okay, so first of all, I would switch notation. I will write mu0 instead of R0, because I'm using RT here, so this mu0 is what I denoted by R0 earlier, and I will rewrite these equations, which are the SIR equation, in this form. Okay, so I will write this ST as the exponential of negative mu0 RT, and I will write I by partially solving that equation. I will basically write it like this, when this S dot is defined here, and then I will keep RT in this way, and I will have these initial conditions. So now, the object that I'm looking at is actually now an object that describes a survival function, or the time until the first relabeling of a randomly selected individual who by time t is not infectious. So it's a susceptible by time t, and this ST is describing that individual's survivability conditionally on something, because basically this, as I said, this ST is not a hazard function simply because it does not evaluate to 0 at infinity, right? There is, as you have seen in this example with the stochastic process, there is some probability that some proportion of your population will remain susceptible. Not everybody gets infected. So that means that this integral over here, this integral is actually, if you take it to infinity, it does not blow up. It's finite. So that means that RT is not equal to I plus rho. In fact, you can show this. So that ST is not really a hazard function, but conditionally on the fact that the individual actually at some point less than infinity will transfer over from S label into I label, it is. So I can basically condition on that event, and then I will obtain a proper hazard function. Okay, so if I do this, I basically end up with what I call a transfer model. So this is basically a way in which I'm thinking now about SIR model. I have 3 compartments, and I am looking at an individual that basically starts in the compartment S, is labeled S, and then moves over to I and to R. And I am concerned about the joint distribution of the times of these transfers. So I would like to know what is the distribution of the time of the transfer from S to I and from I to R. So what I have basically told you is that if I think about ST in this is exponential negative mu0 RT, this is an improper survival function because basically at infinity it evaluates to 1 minus tau, and it's not that complicated to see that tau has to satisfy this equation. So this is sometimes known as the final epidemic size. So in this setting it would be a final proportion of individuals who are not infected, or who are infected actually, but in our setting it will be simply a probability that individual ever gets infected or moves out of the compartment S. Okay, so the individual moves out of compartment S ever with probability tau and stays in the compartment S with probability 1 minus tau. And then conditional on the fact that individual moved out, then this ST will be a well-defined hazard function for those individuals. So I can basically write it, and why is it that this is interesting? It basically gives me a way of describing in a manner that's much more elegant the data that's coming out of an epidemic process. Because now in very large populations at least I can think about every individual following the same hazard function which is described by the SIR equation. But then basically I can think about these individuals as being approximately in the limit being independent. So that means that I have actually IID samples. So I can sample these individuals, or I can follow these individuals independently. And the only difficulty is that these individuals are subject to this hazard. This is the density function of the first transfer, for instance. If I know that this was the hazard function, conditional hazard function ST, then I can basically write the unconditional hazard function, and I can basically compute the conditional and unconditional density. I can basically do all of the standard things. Everything here is smooth, so I have no problems with differentiating things up and obtaining both the cumulative and densities, the distribution functions and density functions. Okay, so for instance, this will be the expression for the first transfer time. So this would be the transfer time from the individuals from the S compartment into the I compartment. And in a very straightforward way, in a similar fashion, I can actually do this for the other transfer. So if I called the first transfer E, that's TE, it's for exposure. So if once you are exposed to an infectious individual, you're transferred over to the I compartment, but then from the I compartment you get transferred over to recovery. So this is transfer to recovery, TR. So that's actually again directly. There is a nice way of showing this, but I don't have time, so we will just sort of have to accept it on faith. But conditionally on the fact that the unit fails, the joint probability distributions of these two by the SIR equations, it has to look like this. So I'm looking at the number of individuals who are not in the initial batch of infectious, and they are decaying according to this exponential, according to the law of mass action. So that basically tells me that the joint probability distribution of these times looks like this, but now it's a product of two densities. So that means that I have independence. So that means that I actually have independence of TE and the holding time and the E compartment, which is TR minus TA, which is not surprising. This is basically just telling me that as soon as I have entered into the I compartment, it will take me exponential amount of time to recover. Okay? But that basically gives me a joint probability distribution for TE and TR, and it's actually quite simple. So I can simulate from this random process, and this is an example. So the way in which you're supposed to read this, you're looking, and I've only done, I think, 100 histories here. You're looking at a single individual vertically. So that individual got infected at this time, and that got transferred over from infectious to recovered at this time. This individual was infected at this time and got transferred over. So for every vertical line here, I will have two dots, which are representing these two random times. And if I plot this, you basically see that obviously they recover the SIR curves, the Kermack-McKendrick SIR model, because basically that's how I have generated. So just by looking at the empirical distribution of these individual histories, I can recover the entire shape of, and in particular the distribution and the parameters that are underlying this. So basically the way to do this is by means of the likelihood function. So I can just write out now, based on the fact that I know what the survival function looks like, and I know that I have independence between these times of entrance and the time of the total time spent in the I compartment. I can basically write out the joint distribution function for individual history. So if I have individual who is basically up to some specific time, I'm looking at these individuals, and I'm looking at K of them that failed at these times. I look at some of them that recovered and some of them that did not. I basically end up with the likelihood function, which looks like this. So this is now I'm in the setting of the classical survival analysis. The only difference is that instead of using a specific survival function, I'm using a survival function which is given by the differential equation. So we call such systems, at least I call it with my students, survival dynamical systems. They're basically describing the hazard of these transfers by means of a differential equation. And SIR turns out to be one of the simplest possible models of this type. Okay, so basically what this means is that it's possible and potentially interesting to build these types of models, because they give you a different way of looking at epidemics. Instead of looking at counts, you're looking at the survival times, and you're looking at the failure time. Okay? There's nothing really in what I just told you which is specific to mass action. I can play exactly the same game as long as I have a version of the law of large numbers on some different objects. So I don't have time, as I predicted I won't. But the general idea, and potentially much more interesting idea that this can carry over, is when you have a random graph. So this is one of, again, the simpler ways of constructing a random graph by a so-called configuration model. So it basically means that I am taking a probability distribution, a discrete probability distribution, and I use it to generate degrees on the number of nodes. And then I will connect these nodes uniformly at random, okay, based on the number of these half edges that are available. So this is a standard construction of the configuration model. It's equivalent under the Poisson degree distribution. It's in the long run equivalent to Erdos-Renyi graph. So the idea here is that we basically could use some of the results that have been obtained on the law of large numbers for these kinds of structures to basically repeat exactly what I did under the SIR model. So that's interesting, because that's actually more likely to be useful for things like transfers of various types of infections, for instance, through social or through contact networks, or some more complicated types of modeling transmission than what I have used so far. In fact, in our dealings with these kinds of objects, we have allowed, for instance, the individuals who are neighbors of infectious individual to drop connection, which is a reasonable thing to do. Basically, once you are in the neighborhood of individual who is infectious, you would expect to change behavior. So that means that with some probability you could drop connection. So we have these models that we call SIRD, and we supply these. So I don't have time to talk about this, but we basically, under certain conditions, which are actually quite funny and interesting, it turns out that for some class of these degree distributions, you can obtain a very nice version of the law of large numbers, which is not much more complicated than the SIR model. And using this law of large numbers, we can, again, in a very similar fashion, generate the idea of a survival function. In this case, the survival function is actually, the cumulative survival function actually looks like this, when D is the number of edges which are S on one and I on the other node. So this is these are the edges that are connecting S's and I's. This is the types of objects that you need to count in these graphs to be able to understand the risk of an infection, and S is the number of susceptible. So the hazard actually has more interesting form in this case than in the SIR case. So again, this is just a way in which, under the assumption that you are operating within very large population, you can drastically simplify the description of your probabilistic model that generated the data. So then you can basically use this to do inference on the parameters under the assumption that your population was sufficiently large, then this limiting model was actually related to the original model. So this certainly wouldn't be appropriate if I had only 5 people or 6 people, because then the stochastic effects would overtake any kind of law of large numbers. But as soon as I have some notion that the law of large numbers is likely to hold, so the population is sufficiently large, then I can attempt to do it. In the case of Ebola, for instance, the number of individuals at risk was assumed under most circumstances to be close to 10 million. So then this is population that's large enough. In some simulations that we have run, it seems, because of the sort of issues with the Jensen inequality and the curvature of these likelihoods, we might have trouble even when we're looking at a couple thousand. But beyond a couple thousand, it seems that we are getting quite good agreements of these limiting models with the finite models, for instance, from the Gillespie, obtained from the Gillespie algorithm. Okay, so just one more slide. So what I'm proposing is slightly unconventional, maybe, because I am suggesting that perhaps a good way of trying to monitor and analyze epidemics is not necessarily by looking at the counts of individuals who are infectious or infected over time, but rather try to pick up these initial individuals at random, I call them human sensors, and try to follow that individual's status over time. And then find out with as much accuracy, as closely as possible, the timing at which these individuals transferred over to different compartments. So the idea here, underlying idea, is that somehow this time of transfer tells me about hazard that's being, or this infectious pressure that's being exercised on that particular unit. And if I can capture that information, then, in the statistical sense, this is a more efficient way of estimating parameter than trying to capture with potentially very, very large errors the counts that are of the entire population moving forward. So instead, I'm assuming that I'm working with infinite population, and I'm just looking at times of transfers to these different compartments. Okay? So this is this human sensor network. And interesting enough, I don't know whether this is something that necessarily supports my argument, but I mentioned that yesterday to some people, that You know, in 2016, everybody was very surprised about the results of the election in the United States. We have had a president that was an underdog, and not that many people thought that he actually could be elected, except for one poll. There was one poll that was run by the Los Angeles Times, which was run very unconventionally. They have basically had a number of people, about 50 or maybe up to 100, that they contacted early on in the election. And then they kept calling them and asking them how they are changing, whether they're changing their views and what's happening, whether they continue to support one or the other candidate. And this was the only poll that actually has correctly predicted that the results of the 2016 election. And again, you know, they have used something very similar to what I call the human sensor. It could be a complete accident. You know, I've done applied mathematics for a long time, so I understand that most of the things that happen in the world don't happen because of the mathematics, but they happen because of lots of other things. But I would like to think that this is maybe an example that says that this is an effective way of trying to extract information, and it might be useful. Okay, so. Just a couple final thoughts. So the idea here is that the versions of the Selecki construction at infinity might be useful, and that these kinds of methods can be relatively straightforwardly extended to what I call these survival dynamical systems. So lots of compartmental models will be in the class of SIR-like systems, for which you will be able to explicitly write out what these transfer times should look like. For instance, under mass action, it's actually quite simple to see that, you know, as long as you assume exponential decay, it basically is equivalent to saying that there is, you know, exponential holding time independent of the entry time, and that simplifies many of these models to the point that they are becoming much more tractable. Okay, so this notion of sentinel network, maybe this is something that we should consider. And at the end, I would like to thank two of my collaborators and colleagues who've worked with me on this. Bosong, who is sitting here, thank you, and my postdoc at Ohio State, Washur. Some of you have seen at Sydney. He's done some really fantastic work on this. There is some interesting aspects of this work which are probabilistic that I don't have time to talk about, but generally speaking, because of the fact that you have this probability of moving or not moving out of this S compartment, you can actually express this entire problem relating to hazard in terms of the underlying random measures. And these are interesting random measures because they're not Poisson, they're binomial random measures. So you can think about, for instance, interventions in this setting if you think about these models and in terms of the action of a functional on a random measure. And that actually is a useful way of thinking about interventions. So because then you have a nice stochastic optimization problem. So I don't have time to talk about any of this, but I just want to bring up that there is some nice underlying probability structures as Washur and Bosong have been helping me to uncover. So we'll continue to work on this. And I would like to thank my institutions and the National Science Foundation for funding some of that research, as well as for various other entities that have allowed me to do what I really like to do. So I am grateful. And last but not least, there is a conference in Poland that I am helping co-organize, and I would like very much to encourage you to take a look at the website and see if you would be interested. We still have some, I think, number of spots available. There will be lectures, and I'm hoping that there will be an opportunity to have a specific session about these survival dynamical systems as part of the program. So there will be some interesting opportunities. Then I hope that I will be able to show some examples of how this actually was applied to the Ebola data, which is a bit surprising. So I would like to thank you with this, and I will be happy to take questions.